Welcome to Optimus Solutions webinar session, and this will be a session on the introduction to industrial filtration equipment, such as baghouses, et cetera, et cetera. Today I have Mr. Jack Clements, one of the industrial experts in this technology, with me today. Mr. Jack Clements is an expert in dry gas fabric filtration, pulse check technology. He's worked on some of the cutting edge of filtration applications. He's been in this industry for 45 plus years. That's a lot of years.
Some say too many.
We just counted up his patents. He's got 37 patents related to this industry, related to filtration technology. If you guys want a list, feel free to email us. I'll have my contact information at the end. So overall, what are we talking about today? What's in this presentation for you? Why does it matter? So first off, one of the things I've always wanted to know was what are all the different air filtration systems out there? What are their pros and cons? Why select one versus another? We will go through some of these slides. The next natural question is, what are the parameters, especially for baghouses? Air cloth ratios, velocities, internal velocities, interstitial velocities, et cetera, et cetera. And what are some of the new stuff out there? What are some of the differences out there, pleated versus bagged? And we will go through these three main topics. So without further ado, I will intermittently have discussions with Mr. Jack Clements, and I will let Jack take it off from here. And any questions that we get, we will interrupt you.
All right, it's fine. Thank you very much, Tom. My background is, as Tom said, I've been in the industry a long time. Various positions as chief engineer, technical director, that type of thing, and mainly in hot gas filtration. But that said, also in pneumatic conveying, where we're talking about process type filtration, smaller collectors, and then even the larger gas turbine inlet filters. So, got fairly wide experience in cleanable dust collection. And this focus on this whole presentation basically is on cleanable gas, where you're using some method to intermittently clean or have a continuously operating collector rather than a static furnace type filter. So anyway, one of the natural questions is why do you have particulate control or dust control, fabric filtration, however you want to term it? Mainly, there's three areas: collect product, and this would be more of a process-related type application where you're generating a usable, sellable, valuable product, and then the second, probably most common for larger utility type baghouses or nuisance collection, where you're complying with government regulations, and that could be OSHA, it could be MSA. Yeah, just basically where you're required to control emissions to a certain level, and then to protect resources, which is somewhat related to regulations, but it would be to protect personnel, prevent toxic materials from being released, that type of thing. So anyway, that kind of covers why we want to apply or use or select this equipment. And I'm going to be talking mainly about primary collectors, where you're collecting it's the final filtration level, not necessarily some of the intermediate collection levels. And the type of collectors we'll be talking about initially will be mechanical collectors, electrostatic precipitators, ESPs, scrubbers. I'm talking about wet scrubbers using water or solvent. And then baghouses, also called fabric filter collectors. Typical industries where these types of devices are applied, some of them pretty obvious. Food and pharmaceutical processing. Food, you have both nuisance dust to prevent dust from getting from the atmosphere, but also your grinding, crushing, pulverizing, conveying material that you need to separate the dust or particulate from the airstream. And then in chemical plants, you're doing the same thing: grinding, crushing, that some mass transfer and that type of thing. Then in consumer products, there's a lot of cosmetics, detergents, soaps, that type of thing that are during the process, or some milling involved, or some kind of size reduction of products. Mining, obviously, that'd be the same thing, where you're taking rock or whatever and grinding it and extracting it later chemically or whatever. One of the big uses for a lot of the fabric filters is in rock dust. We're talking about cement production, lime, asphalt, hot mix asphalt, coal, that type of thing. Agricultural products, that could be at the farm level, where you're bringing produce into a grain elevator, and then it's taken on to food processing, that type of thing. Primary metal processing could be alumina into where you're grinding and processing or removing fluorides from the alumina, and batteries, and also in foundries where you have sand handling systems and that type of thing. Wood, furniture making, wood working, where you're sawing, cutting, also engineered hardwoods, where you're shredding materials to make into an engineered hardwood. One of the big uses would be utilities, boilers, where you're also handling the raw coal at the mine level all the way up to the actual power plant. And then once you burn the coal, then of course you have fly ash that you have to deal with. And metal fabrication, and I'm not going to be talking so much about that aspect or the equipment that's used in that. A lot of that is cartridge type, smaller collectors, and what I'm going to be talking about more is the heavier, high loaded, hot gas type filters that be used in a more heavy industrial situation.
So it sounds like from this is a very wide range of products and processes, and it almost sounds like each one has a small difference or a big major difference to really, you have to really know your understanding of that process to really solve the problems.
Yeah, I mean, you're exactly right. I mean, there's such a broad range of what's needed in each one of these industries, and not only each industry, but maybe a certain step in the process. Mm-hmm. I mean, a cement plant could have 20 or 30 different dust collectors on it that are doing things from the final packaging, where you're controlling the dust from packaging the cement, to all the way to handling the raw products, to the flue gas that's after as part of the kiln emissions. So, and every one of these has a very specific requirement, and so that's one of the points I'm going to try to make later on, is that you've got to ask a lot of questions if you're going to build a piece of equipment to handle any of these uses, and the customer has to be aware of what's critical to the selection of the equipment. So yeah, it's very much custom equipment. If we talk about pre-collectors, and all of these except the last one are basically utilized mainly as pre-collectors. The main purpose we're trying to serve with a pre-collector is to relieve the dust load, or to filter out, or to classify some of the usable products. In other words, you might have a process where you have a usable product that is a maximum size or a minimum size, let's say 100 mesh, and so you may want to use a settling chamber or a baffle plate type collector that's integral to your equipment to remove that product and not convey it to the baghouse, where you then have to separated from the finer product that might not be usable. So in a lot of industries, probably the knockout box and Cyclone are probably the two most common collectors that are used as primary or as secondary collectors are pre-collectors. The Cyclone especially in the 50s and 60s was used a lot as a final filter. And you have the problem there that on smaller particle sizes, you might only be 80, 90, 95% efficient, which after all the legislation and is not going to meet current requirements, but it's still very useful in separating larger products or classifying it.
So would this be normally, is this a requirement, or is this a little bit less expensive just to have this kind of coarse filtration first and then have?
We'll touch a little bit on that in some of these later slides, but yes, I think it's more if you you can relieve the dust load on the final collector. You may have to use less compressed air. You may be able to get by with a little bit different type of filter media, that type of thing. But on the side, I'm also going to caution you. You can in some situations take out too much of the coarse fractions, and actually cause problems with the primary collector. And we'll get into that a little bit. But I think the primary benefit, like on an asphalt plant, especially on a counterflow or on a where you're not mixing asphalt in the drum, which also collects some of those fines. But you can't have too many fines in hot mix asphalt because it affects the quality of the road. So you want to remove all of those larger products, and they'll be wasted or whatever. But in a lot of cases, you're collecting valuable product that, whether it's cereal or some part of a food or pharmaceutical product, that you won't have to do any further work on. It's already the right size, and you don't have to separate it from some of the smaller product. So this is a logical choice for that type of application. Cyclone, to talk about some of the advantages and disadvantages of Cyclone collectors, there's no moving parts. It's simple. It can be fabricated by almost anybody that has simple fabrication methods. It's able to handle very high temperatures, only limited by whatever the metal that's used in the construction, and you can combine a large number of smaller cyclones to really increase the overall efficiency of the collector. One big disadvantage is the airflow through the collector varies. It drastically affects efficiency, and if you have a process like a combustion process where you're constantly varying the airflow in order to meet your combustion demands or your cycle demands, then your product is going to go all over the place. You're collecting, or the amount of product and size. It's not suitable for sticky materials, and if you're dealing with a very abrasive product, then you can have a lot of wear issues. So the other thing that if your efficiency drops off very dramatically with smaller particle sizes. So if you have a lot of small particles you're trying to collect, it may not be the best choice. And low density products like wood shavings and things like that are difficult to capture and recirculate back through the system. And if you look at the typical cyclones, if you have a standalone or a large diameter cyclone, they're probably limited to about 10 or 15 foot in diameter, or then you start having a lot of bypass. And then also, in order to make them more efficient, you can, like I said earlier, combine them into a multi-tube cyclone where you have many smaller cyclones stacked together, and you can achieve efficiencies 95% or more on, let's say, below 1 micron or below 5 micron. So there's still a workhorse of industry, but still not usually considered a primary or final.
Yeah, you can get most of it.
Yeah, it's polishing, sort of a polishing situation. The other technology that it was used particularly in mid last century were wet scrubbers. And when I'm talking about collecting product, I'm talking about particulate, not necessarily mass transfer, adsorption, or absorption, where you're trying to do more than just collect a solid particulate. And so I'm limiting the discussion today to that type of application. So wet scrubbers have a lot going for them. You're able to handle sticky hygroscopic materials, hygroscopic rather, and then combustible, corrosive, explosive materials. And these are particularly valuable type of collector to use for coal or where you're handling a metal dust or something that is extremely explosive. They're very good, and they're used a lot for that. They're also for collecting particles that are difficult to remove when they're dry. And then also you can have soluble gases and things like that you can collect. They'll be collected in these filters that wouldn't be collected in a dry filter like a Baghouse.
With these liquids in the scrubber, is that normally water or
it can be it can be a solvent in the case where you're trying to remove some kind of a soluble product that you're trying to recover or you're trying to prevent from getting to the outside. And you can do you can add you can add reagents rather to absorb sulfur oxides, or there's things like that can be done with a scrubber that make it a very versatile tool. Most of the scrubbers used for particulate control are the Venturi type scrubber. We'll talk about some other types here. Venturi scrubber is used as a primary collector, might have pressure drops across the collector of 12 to 40 inches water column. So you're talking about quite a bit of compared to some other types of collection equipment. Very high energy use in this type of equipment. There are, if you look at different types of scrubbers, the very simple one on the left here is just basically you're spraying. You have water jets that are spraying finely atomized air or finely atomized water into a dust stream, and so your capture mechanism, your pressure drops are fairly low, your efficiencies are fairly low. Then you go into a more higher energy type scrubber in the middle there, where you have some spinning, some disc, and some different ways to improve the efficiency, and you're progressively using more energy to do that. And then the final, illustration on the right shows a Venturi scrubber where you have the very high energy usage, but they can be very efficient. And they're also very good for high temperature, gas streams, because you can actually cool the gas stream as part of the process. Advantages: low capital cost. They can treat the high temperature gas streams, and they can collect really sticky products, and no secondary dust sources. So disadvantages: you might have to have a pond or a tank or recirculate. You're using a lot of water that may be hard to get rid of once you've got the pollutant involved with it. And if you're using, you're polishing all the surfaces inside. So if you have acidic gases, you can have a lot of corrosion and issues with that. And then usually you have to have a cyclone or something to take out the heavy, to reduce the dust load on the filter, or on the collector rather. Of course, water pollution is an issue, and it requires freeze protection. Obviously, you can't operate, operate them at low temperatures without having freezing issues.
So it almost sounds like you want to use wet scrubbers if you need to, not because you want to.
Right. A typical use of there's a lot of them are used for really small dust streams, like if you're producing cereal where you're using sugar to your coating materials. Obviously, they're very good for controlling that. You couldn't put that in a dry collector. But again, they're limited by they're not all the, especially the lower pressure drop collectors are not very efficient. So, but they have their place, and they're still used worldwide for particulate control. The one of the probably the most common types of collectors that especially used in utilities, or maybe especially probably in the 1960s through 1990s, were ESPs, electrostatic precipitators, and basically you're putting a charge on a particle of one polarity, and then you have collection plates of the opposite polarity, and you're collecting the products on either plates or wires, and then periodically you're wrapping them or doing some mechanical action to dislodge the particles. The real advantage on these things, and the reason why they were used a lot at cement plants and large volume applications like utilities, is they're very low pressure drop. Because the velocities through the collector have to be so low for the particles to be collected by electrostatic forces, then you're at laminar flow. You're maybe 200 or 300 feet a minute through the whole collector, so you can handle large volumes of air at very low pressure drops across the collector. So they're very economical. The problem comes with if you have the resistivity of the ash that you're collecting changes. In other words, one of the problems with power plants when they switched over to some of the lower sulfur coals, the resistivity of the fly ash changed, so the efficiencies dropped dramatically. And they also they're not very, once they're installed, it's very hard to make them increase the flow, the capacity, or make changes to them. They can't control gaseous emissions. I mean, they just simply are particulate, and they have the capital initial costs are very high, and these things are huge. If you look at a typical utility boiler application, these are football field size collectors, and one nice thing about them, they are, since there's no pressure drop to speak of, they're not structurally, they don't have to be really, almost like a building is basically what you have, but that prevents them from being, in some cases, converted over to other higher efficiency type collection equipment. They're really low operating cost, they're durable, they last for years, and they can have very high collection efficiencies even for small particles. But for the most part, the newer legislation that has dictated lower emission levels, they can't meet those levels of efficiency.
So this sounds like if you got a fairly small group or small output and it's constantly changing product or specifications, this probably isn't the best.
No, it's pretty much a single purpose type piece of equipment. Now, there's a lot of like smaller. They should go back a slide there if you don't mind. There's a lot of ESPs are used in point of source type collection, for specific gas streams. I mean, if you go to a McDonald's or Hardee's, they probably have a small ESP on their grill under discharge from, because they're collecting smoke, basically, but that type of thing. So there are a lot of smaller ones that are used a lot like the wet collectors we talked about, but by and large, most of them were very large because of the advantages they have with, low pressure drop and that type of thing. So the next technology is probably one of the oldest technologies for fabric filtration is the shaker baghouse. And I think there were some of these around even in the early 1900s, probably on metal collection and fume collection. up until the 1960s, probably was the most common type of collector that you might encounter in the industry. And typically, the big difference on this type of collector is that the gas comes in through the interior of the filter, not not on the outside, as we'll talk about later on some of the filters. So you're actually, all the incoming dust has to, or the airflow and dust go up through the internal through the tubes. And these are intermittent type collectors because they can't be, you can't have filtration taking place during the cleaning cycle. So you would have to, typically these would be in compartments. There might be a baghouse that would divide it into several compartments or separate modules, and that module would have to be isolated and taken offline, and then a mechanical shaking mechanism would then cause the dust to dislodge and fall into the hopper. So these, and again, these were they were very effective. It's simple. The collection efficiencies could be very high. They did operate at very, and we'll talk about this air-to-cloth ratio factor, but it basically means that for every, they have to operate at very low velocities. The dust through the fabric has to be in a neighborhood of less than 2 to 1. And you can have low DPs and you can collect fine product, but they are limited. They are big because it takes a lot of filters, a lot of filter area. The maintenance can be very, very expensive because you're shaking, you have mechanical parts. It requires people to enter the compartment to do maintenance work, and they're not really very good for heavy dust loads, because if you also think about it, abrasive dust, everything has to come through the bottom of the filter, so they can you have wear issues if the velocities get too high. So there's still a lot of these around, but they're probably not for a high volume, varying flow type collection or system. They're not really the first choice. Then you could, the next step up, and probably the next step up in technology from shakers, chronologically, were the reverse air low ratio baghouses. And these, on the same way with the as a shaker, the dust collection takes place inside the tube or inside the filter. And these are typically, instead of shaking, they are typically a module is isolated, and then either a pressure fan blows air in the opposite direction of filtration, or in some cases a negative pressure in the system draws air in, and they might even be combined with shaking. There are some units that have both shaking and reverse air. And the big problem here is that they're usually talking about fairly long tubes, maybe even 30, 40 foot long. And so you have to have rings, metal rings sewn into the, at various intervals, keeps the filters from collapsing and trapping dust during the cleaning cycles. And these were used a lot in power plants as alternate to the ESPs up until the last few years. And now, typically, most of these have been replaced by the pulse jet type collectors. There's some other types of reverse air type collectors that they're using a little bit more vigorous cleaning system, much more vigorous cleaning system than the ones we just looked at. They're in use today, and they have the round collector on the bottom here. There's usually 3 different types of cleaning mechanisms associated with that collector. It can be a rotating arm that has a fan attached to it, and the cleaning air is applied to that fan. It can be a pulse type system where there's actually a PD pump providing backflushing air that is usually directed to a single row of bags or a certain area as it rotates. The other type of the collector in the middle is kind of a hybrid. It's used a lot in plants where compressed air might be an issue quality-wise, and that's true on the first one too. and it uses air from the atmosphere, relying on the negative pressure in the baghouse to pull back air into selected compartments. I won't dwell on that a lot because it's kind of a specialized piece of equipment. The equipment that I want to talk about mainly is on the right here is a pulse jet collector. And here we're using compressed air to backflush and clean. And this type of filter is really probably the most commonly encountered piece of equipment, control equipment in the world now. It has a lot of advantages. Can arbitrarily be classified in 3 ways. Our equipment is configured, sold in 3 different kind of categories, and it all has to do with the pressure of the air used for backflushing. And these are kind of arbitrary because they change a little bit, but the low pressure, high volume are typically cleaned using PD pump or a Roots type blower, whereas the medium pressure and high pressure low volume are typically compressed air, using compressed air. All right, in some cases it can be a gas if you're dealing with could be a CO2 or nitrogen or something if you're dealing with a combustible atmosphere.
So if I had to break it into chronologically 3 progressions, would it be we start with shaker, then reverse air, and now pulse jet?
That's kind of the progression. I mean, there's obviously overlap in the use. Right. That's true.
And the pulse jet now is the main.
It's the main one. I mean, there may be instances where some of the other technologies, because of very specific system requirements, may be still the preferred method, but this is the most commonly encountered, method these days. And we're talking about applications that range from little bin vents that you see here on the lower left, just maybe have 1,000 CFM capability, maybe only 16 or 20 bags, all the way up through the large utility style filter that might be filtering a million and a half CFM. And obviously those things require modules, mainly because in order to do, a utility typically has to operate year-round, 24/7. So in order to do maintenance or to take something offline, they need to be compartmented in order to be able to do that. Plus, the cleaning sometimes is done offline. You take a few of the modules offline and reverse cleaning, and it's to assist in the dust removal. So anyway, they're typically modular or compartmented style collectors. Cement plants on the right use larger collectors also, not the size of utility, but you're talking about large gas volumes. And then on the lower right, that would be like a 25 to 100,000 CFM type collector to be used on rock drying, a variety of
asphalt,
on kilns and that type of thing. Smaller industrial boilers maybe. The pulse jet, the different. When we're talking about a reverse air unit, excuse me. The reverse air unit with the fans or the other methods of cleaning may have a few seconds, several seconds, or maybe minutes where the backflushing takes place, and this obviously decreases the effective filter area that's online. The pulse jet, the cleaning takes place with a short burst of compressed air. Now, the electrical on-time or signal is usually 1/10 of a second, but the effective cleaning valve opening, valve closing is probably 1/4 of a second. So anyway, you can have filtering taking place online without effectively affecting the flow. And the cleaning is actually, the unit is online, the reverse pulse overcomes the flow through the filter bag and has enough energy to actually create a shock wave that removes the dust. Very effective, very cost-effective cleaning mechanism. And the cleaning cycle is regulated by a remote timer connected to a solenoid valve. And this can be done from very simple control systems all the way to PLC and computer control systems. And each, the bags are usually cleaned in row by row, and we'll see here a diagram. Typical dust collector baghouse on the left here might have anywhere from 5 to 100 rows of filter bags in it, and each row has a pipe located over it, a valve attached to that pipe, a pulse valve, and when that particular valve is associated with the row pulses, then you get the action you show on the right here, where for a quarter of a second the bag inflates, dust is dislodged, and then the next sequence, so you might clean the 4th row over from that, the 8th row over from that.
You don't want it next to each other.
You don't want the dust just jumping from a clean bag over to a dirty bag, or a dirty bag over to clean. So, yeah, you want to stagger to. I mean, a lot of collectors are set up where they sequentially clean, but I always like to have some separation during the cleaning. We're going to talk about some of the things that are important to the design of a baghouse, and it's important for the end user to convey what they're really trying to do with a piece of equipment and what's critical to them, to the designer of the baghouse. And the designer of the baghouse is going to use that information, and we're going to show some typical data sheets for accumulating that data or that information. But they're going to use that information to select the material, the air to cloth ratio, or how much material is going to be used for the gas flow involved, the upward velocities in between the filters and in the housing, the inlet of where the dust is going to come in, what kind of cleaning mechanism is going to be used, and then ultimately how you're going to remove the dust, whether it's going to be a screw conveyor, simple hopper, that type of thing.
So to quickly summarize, so what we just did was we chatted about the different types of air filtration systems. You can have a pre-collector, be related to the cyclones, et cetera, et cetera. You can have the scrubber systems, you can have the ESPs, you can have the baghouses, and we'll chat a little bit about the progression on the baghouses from shaker to now the pulse jet. And now what we're doing is just taking all those considerations, and this is probably a little bit more geared toward the baghouses, right?
It is. I mean, the list here is, but when we're talking about the dust properties and the description of the process, that's pretty much universal. Depending on no matter which cleaning mechanism you're going to pick.
Okay.
But these are obviously for a reverse air baghouse is the main design considerations.
Mm-hmm.
One thing that really affects the efficiency and the ultimate pressure drop of a collector is the size of the particles you're going to collect, and it's not only the range, but also where the particle, the distribution of particle sizes is really important. In other words, if you have a very coarse product, particulate, combined with a very fine product and nothing in the middle, that's altogether requires some different considerations.
So this is where if I were the plant or I were someone designing, these would be the things you would start going through your checklist on. Okay, well, if I want to go from scrubber to baghouse or from baghouse to a bigger baghouse, here's the data I'll probably start needing.
Right. I mean, it's important to know that, particularly on the distribution, how and where that distribution is concentrated, and particularly on the small fraction, just how fine is it, and what percentage of the total dust load is that fine submicron, below micron size, or even maybe 5 micron. The air, when I say air gas, I mean, air is a mixture, a mechanical mixture of gases. So, but in a lot of cases, we're collecting combustion products, which, aren't air, really technically aren't air, I mean, because of the constituents. So anyway, when I'm using that interchangeably, gas or air. Obviously, it's important how much moisture content's in the gas stream. Are there any corrosive elements? Is there anything that might change the dew point? I mean, if you have an acid present or a base present in the what you're collecting, the material you're collecting, that can alter the dew point dramatically, especially on the acid side.
Yeah, or they just have sometimes there's just too much moisture and you're like mudding up the baghouse.
Absolutely,
just a big headache.
And that's a good point, because a lot of these collectors are on dryers, and where you do have large amounts of moisture. And obviously, for a dry dust collector, for a fabric collector to work, you have to be below the dew point. And that means, it's critical to know what those lower temperatures or ranges can be, because the designer has to look at when you're operating in the wintertime, your exhaust temperatures might be 15 or 20 degrees or 30 degrees lower, depending on the collector. So you might even be pushing that envelope a little bit more, with that. So that's important to know what those ranges are. And it gets down to where these collectors are going to be located. Are they going to be located outside, and are they going to need insulation? Are they going to be, if you're inside a building, obviously there might be space constraints and heights constraints, and you might choose a top access type collector where you have unlimited space. But if you're under a mezzanine, you might pick a bottom access type collector. So these are all the energy environmental considerations. Basically, are do you have a compressed air source available, or what? Environmental considerations are what we just talked about, outside, inside, where it's going to be located. And then, are you going to use the product? I mean, is it a nuisance dust that you're going to just have to somehow dispose of, or is it a usable product? And the outlet emission limits, where you're talking about maybe having a plant or a collector located inside of a building. So you have personnel that, obviously you have to meet the OSHA requirements. Or if it's a toxic product, you're going to have to pick it. It really affects the selection of fabric. And if there are any application-specific specific requirements. And is this a 24/7 operation, or is this a cycle, like a bag? You might have some applications where the collector is only used once a day. You might be loading a pneumatic truck, sand into a bin once or twice a day, so the collector only sees limited use. So you might be able to really push the limits on the sizing. Once you know some of this material, this information, then you can pick a fabric, filter media. And probably the workhorse of industrial filtration is polyester. And that has a limit of 275 with the fabric and 250 with some of the other more rigid products. It's good for most things. This chart shows poor moist heat, but it can be used in a lot of drying situations, as long as you're not in the upper limits of the 275 and you are below certain levels. And it's very temperature, so the amount of moisture that a polyester bag can handle is very tied into the temperature, operating temperature. Acrylic is not used a whole lot, except for some problems where you are in the higher limits of moisture. Fiberglass is used a lot for boilers and for hot gas applications. Nomex or aramid fiber is used primarily in the rock industry, where you're talking about below 400-degree temperatures. Rhyton's used in the power plants. That's usually on a reverse air baghouse on a power plants, typically PPS or Rhyton. And P84 is kind of a specialty product that not a lot of people are going to be using, but it's used where some of these others products aren't useful. Like Rhyton is not very good at high oxygen levels, so you might have to use a P84. It's not, like I say, it's not a very common fabric. Particle sizes. This chart on the left here just gives you an idea of relative particle sizes for common materials, and you can see that a lot of the windblown dust, is typically over a micron to 100 micron size. So this kind of gives you an idea of what more as you get smaller. Obviously, the difficulty increases trying to control emissions. And just to give you an order of magnitude, a human hair is about 70 to 100 microns in diameter. So we're talking about, for the most part, really small particles when we're getting down to the below 1 micron range. One of the terms I've used and haven't explained yet very well is air-to-cost ratio, and just shortened to ACR. It may be called air-to-media ratio by some people, and it's just simply the volume of air or gas collected divided by the total filter area. So in the case of an example here at 25,000 CFM, and I do say ACFM because we're talking about whatever the at the operating temperature, obviously the volume of the gas is going to be affected. So it's very important when we're talking about designing a collector to know what the operating temperature range can be, because if you have something in a process that varies over a wide range, your volume also varies. So in this case here, 25,000 ACFM divided by, if you add all the bagged area up, 5,000, it's 5 foot. It's 5 to 1. Or the way these units cancel out is 5 feet per minute also. That's not true in metric units, but in expressing it the way we have here, it all, the units cancel out so that that's actually the velocity through the filters. If you look at typical air-to-cost ratios for nuisance type collectors handling fairly light loads, 5 to 7 to 1 are pretty common. Boilers and high temperature applications are usually in the 4 to 5 to 1 ratio. Agricultural dust can be as high as 10 to 1. Easy to collect, type products. Fume, that generated by thermal processes, 1 to 3 to 1, even with pulse jets, they're very low.
So what if it's high or versus if it's low? What does that mean?
Well, if you could, the higher air-to-cost ratio you can go, the smaller the unit can be. The cost-wise, the footprint. But on the same token, if you start pushing the air-to-cost ratio, then your operating pressure drop typically increases. And these are typical baghouses work in a probably a range of 2 to 8 inches of water column. And obviously, if you've got a large amount of gas you're collecting, your compressed air costs can go quite, very, very high. So in some cases, you're better off, even with a higher capital cost, going with even though the collector might operate at a higher air cost ratio, from the energy conservation standpoint, compressed air usage standpoint, you're better off selecting the lower value. The other thing too, I think that the asphalt people, the hot mix people learn this. A lot of collectors were sized 6, 7, 8 to 1 in the earlier days, and what they found was not only was energy issue, was that the more often you have to clean a given baghouse, the more emissions you have. And because most of the emissions occur right after a pulse, after you clean. And if you can minimize the number of times you have to clean, the interval between that, you can also have emit less, you can be more efficient. Because if you take a baghouse operating at 6-to-1 or 7-to-1 with polyester, and you decrease it down to 2-to-1, you could probably have almost that proportion in emissions, eliminating emissions. So it's possible to take even a lower tech bag or filter media and actually increase your efficiencies by not cleaning as frequently, which a lot of people I don't think realize. But again, if you can find a fabric that you can operate at whether it has a membrane on it or whatever, you can have a more efficient or a more expensive fabric and operate at higher air cost ratios. So this is a trade-off, and it's something discussion you have to have at the time the unit is being sized and being configured. The other thing too is, the filter media itself isn't necessarily the primary filtering mechanism. If you take a brand new piece of fabric, they're not very efficient. It's not very efficient at first. Actually, the dust builds up. You get a residual resistance on the filter, and then the dust cake itself acts as a very effective filter. And and that's why the dust cake particle size distribution is very critical consideration in picking the filter media being used. Another factor that's important, especially on these larger collectors, is your bag lengths start getting to be over 10, 12 foot long. Some of these utility baghouses can have 30-foot filter bags in them. And so when you start getting larger, probably over 10 foot in particular in length, then you have to be sure that the upward velocity between the filters isn't such that the air being pulsed off never falls down. If your upward velocity is higher than your terminal velocity of the particles, then you're going to have an issue. And when you calculate this, and some people interchangeably call this velocity cam velocity, but I think that's confusing because some people use that word to describe the velocity below the filter bags, where you don't have. But I think the important factor here is what is that velocity between the filter bags. So, anyways, basically, just the cross-sectional area of the housing, filter housing, and you subtract the area that the bag bottoms take up, and you divide that into the air volume, and that gives you your apparent velocity between the filter bags. And typically 300, 350 foot per minute for most products is probably safe. But if you get into a low density, high filter area particle, then that you can be as low as 50 or 100 sometimes. So that's another reason why knowing all the properties of the dust and the application are important. This is just a typical system. I just showed this to show the principal components in a pulse jet or baghouse, compressed air tank. I think it's important you have a reservoir for a couple reasons: to allow some condensation to take place, to keep that away from the baghouse, and it's very important that you have a clean air, dry air being used to pulse filter with. It's important you have a filter trap or moisture trap and also an oil separator prior to going into the dust collector. Item 10 here just shows a typical the reservoir, the header at where the pulse valves are mounted. There's your controller means of some way showing 12 with a sequence of valves, and then the clean air plenum and the dirty air plenum, and then of course most of these filters are set up as a negative pressure arrangement so that any leakage you have is into the filter and not dust out in the atmosphere.
Puffing on the outside.
Right. So you want leakage, you want clean air in, not dirty air out type thing. Advantages of pulse jet, reverse air pulse jet collectors, very compact. You can operate at usually much higher air cost ratios than you can with the other technologies we talked about. And one good thing is they're stable, and because you're pulsing online and pulsing only a small part of the collector, and by using a small volume of air to pulse with, they're good for combustion processes or air applications that require constant flow and not much variation in pressure drop. Very high efficiency collection, high collection efficiencies are possible. They can operate up to 500 degrees, and even with specialized medias even higher. And the dust inlet can be varied to, depending on the type of particulate you're collecting. Disadvantages, they need dry compressed air. If you're operating in a baghouse in Michigan in the wintertime, you really have to worry about, moisture content in your compressed air. And obviously your inlet air or gas got to be below dew point, or you're going to have mudding or problems, operational problems. This slide here is, probably a little bit better pictorial representation of what a baghouse looks like internally, and it shows you some of the major components we looked at the other slide. Very typical arrangement where you have pulse valves arranged on a header, anywhere from 7 to 12 inches apart, and then each row of bags, everywhere from 4 to up to as many as 20 bags in a row, depending on the valve size.
So really, that B section, the C, B, and D, that's pretty much the key piece, the pulse jet piece.
Right, that's the smart part, I guess, section there. And the real critical thing is where that D, that balloon D shows up. Air inlet. I've seen a lot of collectors that where they may have a an inch connector, pipe connection on there, and people put maybe a 1/4 inch or 1/2 inch hose connection, or up to that, or piping. Mm-hmm. And it's very important that each one of these valves, when you operate, the typical sizes for a dust collector are anywhere from 3/4 inch to 1.5 inches, maybe as much as 2.5 inch valve. An 1.5 inch valve will consume about 4 CFM in a pulse. And you want to make sure your header there, that B there, compressed air header, the pressure doesn't drop down very much to affect the pulse. If you undersize your piping coming into and starve off air, even though the right valve size might be used, it's not effective because you don't have enough compressed air. So that's something to be covered, obviously, in a more advanced treatment of this, but that's a very critical. The quality is very critical, and the size is very critical. Typical applications, everything. These are the pulse jet baghouses for pneumatic conveying. Is kind of the if you go into a plant that's handling bulk material, plastics plant or food plant, there's going to be little dust.
It's still very wide ranging on a lot of applications.
Right. And nuisance dust collection, the things I've listed here, and then really the workhorse in drying, calcining, the hot gas, big hot gas type industrial applications. And this is just what we looked at a little bit earlier. This, just showing that there are other, besides using compressed air, there's other ways to back flush. And then, the next one there is this is the typical information required. And you would need this whether you were sizing a baghouse, a scrubber, or any of the collection equipment. I mean, it's basically, the airflow, what's in the gas, what kind of atmospheres can be working in as a product, explosive. If it's explosive, then that causes, and most products, most organic products are. I mean, people don't think about sugar and coal and
corn, and they get
plastics. I mean, all those things are explosive. If you can burn it, it's explosive for the most part. And even metals, you can have, fine aluminum or magnesium or something. It's very much. So it's important to know if you have any of those products you're handling. And there's very specific National Fire Protection Association and factory mutual requirements if you have any of those products, depending on where they're being used, what has to be done. And whether it's inside or outside location. And then the particle size distribution, a lot of people aren't going to know this, but today with some of the requirements that OSHA has, although some of those requirements are suspended right now or not being enforced, it's very important to know the particle size distribution. And if you've got an explosive product, as a user, you're responsible for telling whoever's designing the equipment what the particle size distribution is, because that affects how explosive the product is. Mm-hmm. And then also just for the general picking the filter media and the air to cause ratios, you have to know that. And dust loading is very important too, because the last thing you want to do is use a dust collector as a storage unit, because that really affects the operation. So inlet loading, how many pounds an hour, what is your approximate dust loading? So those are all important things.
So this is a pretty good, fairly comprehensive set of data you can get for your baghouse. So even if you're not looking for a new baghouse, or this is just good, almost a preventive maintenance, just a halves every month or so.
Yeah, absolutely. Especially if you're changing product or your process has changed. And it's very important that the designer, if you're buying new equipment or you're changing the role of the baghouse, what the process is actually, is it a crushing, grinding, what part of the plan is this used in? Just to say it's a wood, collecting wood, doesn't mean a lot. And you need to know if it's sander dust, is it planer dust? You need to know all those things. So.
Right. Okay, so overall on the design side, the particle size is incredibly important. I know that you mentioned that multiple times.
Right.
And ultimately that determines what media you pick, depending on the sizes. And it sounds like also you got your air to cloth ratio, right? You can have it high, you can have it low. The two competing parameters is you can put more air in or you can put less air in, but that will affect your pressure drop. And it's that two competing pieces will ultimately you pick depending on the application. If you can handle more, great. If you can't, and it sounds like there's no do this, keep this up, that's great. It's more of here's 10 different factors. We need to consider it. And here's kind of that sweet spot you need to be for that application.
That's true. I mean, and you can have, even if you can tolerate a higher pressure drop, like you talked about by maybe pushing the unit, you also have to worry about there's a tipping point. There's a point where the cleaning system is not going to work. It's not going to effectively keep the pressure drop constant, and you're going to lose control. And typically, if that happens, that means the unit has to be shut down, and hopefully you can recover by cleaning offline or reducing airflow or something like that. But and that's why in some cases, some people also think, well, if I have 1-inch valves on here now, I can put 1.5 or 2-inch, and I can get more air through it. Mm-hmm. There is just for a given product or process and concentration, there's a tipping point where all the pressure in the world isn't going to help.
Well, the takeaway, it sounds like, is it's really not a set it, forget it system. You just click a button and your baghouse works. Right. And it's not you keep doing this one thing, it gets better. It really is everything you do has a consequence.
Right. There's modern control systems now that are available that monitor a lot of these things. Whether it's pressure drop but you've got to recognize there's trends taking place. If you've got a baghouse that's been working fine for a long time, and all of a sudden the pressure drop starts increasing on it, or you start having throughput problems, then you've got to look at some of these things and see, factors to see what's changed or what might be affecting it. And it may be just a very simple thing is that the pulse, I've gone out and had the control panel shut off inadvertently shut off on a collector. Obviously that's not going to work very well, but it's just got to be something that, needs to be constantly monitored and has a maintenance program.
Yeah. Well, so this next one, this is the last major piece of that pie, is the types of tech out there. In particular, the bags. There's always the debate on pleated versus non-pleated. So we'll dive a little bit into the technical details of that.
Well, we'll talk about this technology has been around for a while, but it's mainly been in the pneumatic conveying area. I mean, in smaller dust collectors, it's been probably used for a number of years. But what is I think exciting about it is that there's a lot of cases where this technology can be used in existing collectors to increase throughput, and we'll talk about some of those factors here. We're talking about pleated filters. We're talking in this context anyway. We're talking about filters that are designed to directly replace conventional bags that are supported by cages. Mm-hmm. So we're not talking about the large 12-inch or so paper filters that are used for fume control and that type of thing. We're talking about actually taking a bag out and putting a pleated filter in. And you see some of the, on the right, typical bags. Of course, they're shortened for the picture here, but I mean, typically everywhere from 8 to 20 foot long. And the pleated filters over here, both for bottom load type access to top load. Variety, they're available in almost every configuration to replace a filter bag. And if you look at a typical bag, and the one on the right here, that's for some reason the size is missing on this, but if I recall, this is 16 foot long. So you're talking about at a 6-to-1 air to cost ratio, this bag on the right would have a capability of about 200 CFM. The same filter, 6'8" long, the pleated filter, would have, operating at a lower air cost ratio, would have the same capacity. So you're replacing, in this case, a 16-foot bag with a 6'8" bag for the equal capacity. So if you don't have a 16-foot bag, you have a 12-foot or an 8-foot, obviously the advantage is even more. You start getting a lot more flow capability. Just looking at that here, if you look at an 8-foot bag sized, and these are sized at about 7-to-1, you might have 13 cubic foot capability in a 6x8 foot bag. You'd have 75 CFM capability in one of these pleated elements, and all the way up to the.
And the key is the pleat is just a lot more surface area.
A lot more surface area. Now there's some caveats on that.
It's always a caveat.
It's for some reason that's not changing. There we go. There's some, obviously with the pleats, they're going to be a little more susceptible to clogging or filling up with a really wet product. Mm-hmm. And that type of thing. So there's some products that they don't work well with, but actually it's a very limited number of products that they don't work. Because we're talking about pleats now that are a half-inch wide at the top. They're not like a paper cartridge where they're wedged in 12 pleats to the inch. There's maybe 2 pleats to the inch. So we're talking about a wide open structure, and the depth is anywhere from a half-inch to probably an inch is typical. So we're talking about a wide open area there. The other thing that helps on pleated to operate in fairly wet situations is that there are new finishes, and actually oleophobic, hydrophobic treatments that are plasma deposited that every fiber in the filter pack actually has a angstrom thick layer of our material to prevent water penetration or oil penetration.
Angstrom is 0.1 nanometers.
Right, and we're talking about actually a bond, a covalent bond, not just a surface coating.
So we're talking on the scale of atoms.
Right, and it's very effective, and it's even available for food grade applications.
And oleophobic will be
Oil.
oil. Afraid of oil. Hydro is afraid of water.
And there's some standard testing for that measures the holdout, the oil holdout and the water holdout, and that data is all available from the people that supply these things. So, and also they can be treated with conductive means for explosive situations where our metal dust, where you have to have by law conductive medias. And also, nanofiber depositions on the surface would greatly increase the filtration efficiency as well as lower their operating pressure drops. So there's just a huge amount of variety available. Everything from, similar to the chart we looked at earlier with bags, everything from aramid, PPS, polyester, again, is a workhorse. Polypropylene in a limited amount for really wet situations. Glass and very, very specialized applications. And then the PTFE, the film, like you're familiar with sporting goods and stuff, that that have the layer of Teflon type product on it. Those are all available in all those products. So very versatile. A very cost-effective way to take an existing collector and increase the throughput by 25 to 30, 40%.
Right. So these applications will be, you already have a baghouse with the conventional bags, and you've met the capacity or throughput or something. You've hit the limit on the baghouse.
Right.
And this is a way to either extend that life or make a change where you can use that same or retrofit.
Absolutely, and you can also correct issues like if you have a longer filter bag that the inlet duct might not be properly designed, and you have a huge abrasion problems because you're having the airstream directly impact your filter bags. You can replace a 12, 14 foot long filter bag with a 6 foot filter bag, take the filter packs completely out of the abrasion zone. So there's a lot of things can be done. Different length, if you have some issues with cam velocities, you can put longer, shorter combinations in to open up that area for airflow. So there's
okay, cool.
Typical applications, again, a lot like for the filter, almost identical filter bags. The smaller pneumatic conveying equipment, the nuisance dust collection.
Still very wide.
Yeah, so drying, extruding, all the same type of things are used where and another thing I want to mention, people say, well, obviously you can't handle the same dust loads with pleated filters as you can bags. Actually, the most of the areas these were used in originally were in pneumatic conveying systems. And instead of talking about 1 to 10 grains per cubic foot dust loading, we're talking about 100 grains, 200, 300 grains dust loading. So these are not, like a paper filter. You would think those are normally very low dust loading type filters. These are built for heavy duty dust loading. And again, some of the things we talked about. I mean, if you didn't want to increase throughput, but you wanted to reduce your emissions, or you wanted to save energy, you could go in. If you didn't want to increase your airflow, but you wanted to pulse less often, you wanted to operate at a lower pressure drop, then this would be an ideal, solution. And corrects some of the problems, what I talked about with abrasion and excessive cleaning and that type of thing. And the big thing I think that most people are interested in is the increased throughput.
So it sounds like there's kind of three major things that I'm getting out of that is A, if you want to make more stuff,
Yeah.
this is an avenue. If you want to be a little bit more efficient, this is a little, or you're told to meet standards,
Right.
emission standards.
Right. I mean, obviously these filters are going to cost more money than a filter bag.
Mm-hmm.
They replace more than a single filter bag for one thing, but also that if you've got a product that your throughput is valuable and or increased flow to dust collector somehow affects your bottom line or what you're doing, these are very cost-effective ways, methods of accomplishing those goals. And again, these are just it's just a summary of the benefits we already talked about here. And one thing I didn't talk about is that the last item here reduces static electricity discharge risk. If you have a cage, a metal cage that's in a synthetic bag, you've isolated you've got metal that's isolated from your collector, and a lot of people use grounding wires or some ways to do that, but that requires that someone actually, consciously attach a wire to something or it doesn't get broken or whatever. These filters are available for operation of below 200 degrees that you have all synthetic construction, no metal parts involved at all. So they're inherently safe because the amount of the charged electricity can build up on the surface is well below the minimum ignition level of most dust, especially let's say above 10 milligrams or 10 MIE. I mean, they're inherently safe products. So a lot of people that are handling explosive or combustible products will use these things and not have to worry about their maintenance people connecting. And again, smaller footprint. But if you were a new collector, all the advantages of higher flow to a given size, energy savings, less compressed air. They typically operate, because they're operating at lower air cost ratios, the pressure drops are typically lower. Filter can address issues of abrasion, and it's a lot easier to change out a 6-foot filter that weighs 8 pounds than it is to change out a 20-foot bag that weighs 35 with dust on it. So
okay, cool. So overall, it sounds so. The three big thoughts on this is the different types of collectors: Cyclone, ESP, scrubbers, and baghouses. The progression of the baghouses from the shakers to the reverse air to the pulse jet, and there's overlap, but that's that rough. Some of the design considerations, the cloth ratios, the differential pressures, and these all come down to efficiencies and the particular application. And then ultimately we chatted about the depleted versus a standard bag. It sounds like there's a lot of advantages, and I think one of the consequences is cost. And it sounds more and more like if you met the limit and you're at a spot where you need to improve it just that little bit more, this sounds like the avenue to go through.
well, it can be a dramatic improvement in your throughput too.
Mm-hmm.
If that translates into saving more of a valuable product, making more product, then it's just more than a small increment, an advantage.
Mm-hmm. Right. So overall, we've finished the PowerPoints, and Mr. Jack Clements will be a guest speaker in our upcoming Optimus class in between February 5th to February 7th. This Optimus class is the Optimus dryer
class, Intro to Rotary Dryers, all the consequences and education on what that means. We focus on dryers, baghouses, seals, all the peripherals directly related to rotary dryers. This is February 7th or 5th to 7th. We will have Mr. Jack Clements as a guest speaker, obviously in Particulate Baghouses, and we will go much more detail into this. If you have any questions, any concerns, any comments, feel free to contact me. My name's Tom Zhang at tzhang@optimusps.com, or Sarah Ballou, she is our key account specialist. If you can't get a hold of me, you can normally get a hold of Sarah at sarahops@optimusps.com. Well, we really appreciate the discussion, Jack. I think we learned a lot in the three major pieces. Again, appreciate you guys listening to this webinar. Again, if you have any questions, feel free to contact me or Sarah. And if you are interested in directly meeting Jack and having any questions or pick his brain, we do have that Optimus class coming up. Thanks for listening. Appreciate the time and energy you listened to this webinar. Thank you and have a good day. Thanks.